Just let me know when you're able to see my screen, okay? Are you able to see my screen?
Yes, sir.
Okay, so we were
Yes, sir.
discussing complex variables. Okay, that's the first module of your syllabus. You're talking about complex variables. So last class we had stopped at this slide, and we'll proceed. A complex function. Okay, so we're talking about complex variables, and the moment we talk about variables, that means we could talk about functions also. So suppose I have a complex variable z, then we could define a function out of this. So it's known as a complex function. So complex function of a complex variable is defined to have the same power series expansion in z as the expansion. Sorry, suppose I have a real function, okay, which contained x, and this function is f of x, and this function has got a power series expansion. Then a complex function will have the same power series expansion where x is replaced with z. Okay, so in this case what happens is the real and the complex definition, they will coincide when z is real. So for instance, if I have you know about the exponential function, right? The exponential function, that is e to the power x, and you know that the e to the power x, it has got a expansion like this. So e to the power x is equal to 1 plus x squared by 2 factorial plus x cubed by 3 factorial, so on. So we can write this as a summation like this. So what will be the complex counterpart? The complex counterpart, what will happen is f of z, same function f of z, what will happen is just x will get replaced with z everywhere. So we had 1 plus x, so it will become 1 plus z, okay, plus z squared by 2 factorial plus z cubed by 3 factorial, and so on. And it can be written as a summation like this. Okay. So a complex function can be represented in this way. Because it's a complex function, it has got two parts to it. It has got a real part. So let's say I have a complex function like this. Let's say I have a complex function which is f of z, and because it's complex, it will have a real part, okay, of the same function, and it will have a I times an imaginary part of the same function. So this real part of this function, we call it as u, we write it as u, and the imaginary part we'll write it as v. And both u and v, okay, u will be a function of x and y, and v also will be a function of x and y, because z ultimately depends on x and y, z equal to x plus iy. Okay, so here u and v, these two are real valued. Okay, these two are real value, these are real functions, but when you combine them in this way, this real function plus I into this real function, that becomes a complex function. So you can express a complex function in this manner. Okay, so now to understand this a little bit further, we can make use of Argon diagrams to graphically understand what complex functions are. So a complex function, let's say w is a complex function, w equal to f of z is a complex function. So what is this basically? It is basically a rule. Okay, you give a rule, and what is this rule for? The rule is meant to associate one complex number, a unique complex number, and this unique complex number I call it as w, to every other complex number. So we have two Argon diagrams. One is for one is z, another one is w. So let's say I'm having two Argon diagrams. So one is x versus y, another one is u versus v. Okay, so in one Argon diagram, so we have a range of values for the z. So z exists in the first Argon diagram, and w, this complex number, it exists in the other complex in the Argon other Argon diagram. Okay, and this blue region represents the range of values that z can take, and this pink region, it represents the range of values that w can take. So let's say this is a complex number in one Argon plane, and this is another complex number in another Argon plane. So what exactly is this function? Function is a rule which helps us to associate this point to this point. Okay, so we have one point here in one complex plane, another point in another complex plane. So a rule, okay, a rule which helps us to associate that, okay, if this is the z, then this will be the w. If there's some other z value, then it will be some other w value. Okay, so the rule that helps us to do that. So for instance, if I choose some other z value, if I choose this z value, then let's say the w value is going to be over here. So this association between these two set of complex numbers, this is your function, the complex function f. Okay, so complex, to put it simply, complex function is simply the association between two different complex numbers in two different complex planes. And suppose you move in this direction, suppose you change the z, you go like this, it is possible that the z, in the other plane, the complex number, it could move in this way. Okay, they don't always have to move in the same way. So suppose z goes on a circle, this could move in a parabola. But what we need to have, what we need to keep in mind is the points in this plane will have a correspondence with the points in this plane. So this basically is a graphical representation of a function of a complex variable. Any questions? Does anybody have any questions? You can unmute yourself or you can type in the chat. Okay, I'll move forward. So formally, you can define what is known as a limit of a complex function. So suppose a function f of z is defined in a neighborhood of z naught, except possibly at z itself. Then for all I which belongs to the set of complex numbers such that epsilon, so if we take a positive epsilon, there exists a delta which is positive such that this quantity, okay, if z minus z naught, the distance between the 2 points, if it is less than delta, then the distance between the function, the value of the function at z and I, that is going to be less than epsilon. Then we say I is the value of the function at z naught. Okay, so this is the graphical representation. So once again, we have two different planes. One is the xy plane, and one is the uv plane. So in the xy plane, we have z naught, and just like how I had shown you here, so this one has got a correspondence with this point here. Okay, so this one has got a correspondence with this point over here. So if I take z naught here, and then I define something called as delta. Okay, there's something called as a delta, such that the if I take at this point, for instance, if I take this point, let's say at this point the value is z prime, then this complex number, okay, which points from z naught to this one, this complex number will be simply z minus z prime. And if I take the modulus of this, that is going to give me the radius of the circle. So the radius of the circle is delta. Okay, so when I say 0 less than z minus z naught less than delta, that means this one, what does it mean? It means all the z values which lie within this. So all the z values that lie inside this circle. Okay, so all the z values which lie inside this circle, this is the meaning of writing something like this: 0 less than z minus z naught less than delta. Okay, so always remember that this z minus z naught, so something like this z minus z naught, it will represent a radius. It will represent a radius of a circle in the complex plane. Okay, so radius of a circle in a complex plane, it can be represented as modulus z minus z naught. So if I say 0 less than z minus z naught less than delta, that means all the radius which is going to be greater than 0 and less than delta, that means all the points which lie over here. Because if I consider a point over here, then what is the radius? This radius will be obviously less than delta, but it will be greater than 0. So this condition is satisfied. So when that happens, then if suppose I give you give me an epsilon, I can always find the delta such that the value of the function, okay, so this one z, at this z, this will be the value of the function. The value of the function will be such that I can find a corresponding delta such that the value of the function at some z which lies within this circle of this radius delta, that value of the function will lie inside a circle whose radius is epsilon. Okay, and when that happens, we say that the limit of this function is I. So this center of the circle, it becomes the limit of the function as the function tends towards z0. So this is basically the definition of the limit of a complex function. Any question? Anybody? Any questions?
Can you repeat, sir?
Okay, sure.
The
Okay, so let's say we do something like this. Okay, so you give me, let's say you give me an epsilon. You give me epsilon. Okay, and what is epsilon? epsilon is a small real number. Okay, so you give me epsilon. This is what you have given me. Okay, you have given me a very small real number. Okay, then what the limit of a function? What it says is this: if I can give you, if I can give you delta, okay, which is another small real number. I can give you delta in another small real number. So okay, this epsilon, what where have you given me? Epsilon, it lies in the UV plane. Okay, it lies in the UV plane, and this delta, it lies in the XY plane. So you are giving me this. The moment you give this, if I can give you a delta, if I can give you a delta such that, okay, such that I can find, I can use that delta to construct a circle, okay, such that I can use this delta to construct a circle, okay, and in this circle I can find some complex number, so such that when I apply the function to that complex number, it will give me, when I apply the function to the complex number z, it will give me f of z. Then this f of z will lie inside a circle whose radius you have given me. Okay, so basically the point is, if you give me an epsilon which is small, I can give you a delta which is going to be even smaller, such that all the z inside will lie inside the circle which you have defined. So you see, epsilon you have given me, that means you have defined a circle here. Then I can always find a delta in the other plane, which is going to be a circle, such that in the corresponding circle, all the z values which I find inside the circle, all of them will lie inside the circle that you have defined. So you make this epsilon smaller, I can always make the delta smaller. You make epsilon even smaller, I can even make delta even more smaller. So if we can keep on doing that, then we say the value of the function at the center of your circle, okay, because you have given me this epsilon, the value of the value of the number, of the complex number at the center of your circle, which is I, that value happens to be the limit of the function at the center of my circle. So this is my circle, this is your circle, you have given me an epsilon. I can always find a delta which is so small that all the points which lie inside this circle will necessarily lie inside the circle that you have defined. If that is true, then the center of your circle becomes the limit of the function of my circle. Does that make sense now?
Yes, sir. Yes, sir.
Okay. So if you can do that, then this becomes a limit. So this is the definition of a limit of a complex function. Now moving forward, the derivative of a complex function. The derivative of a complex function is defined in the same way as derivatives of real functions are. So f prime, okay, f, we can represent a derivative as f prime, which is df by dz. So df by dz is simply delta f by delta z, where you take the limit as delta z tends to 0. So then this, what is this delta f? Delta f will be simply, let me draw it, let me show you graphically what happens here. So let's say this is the complex plane. Because when you're talking about function, we need to consider two complex planes. One is the xy plane, another one is the uv plane. So this is the plane for z and this is the plane for f of z, right? So here I have a point, I consider a point here. So this is the point z. Correspondingly, there'll be a point which is f of z. Now what I do is I make a small change in z, okay? So z, I make a small change. This point is, now remember how we represent complex numbers, we can represent them using vectors like this, right? So this is this arrow represents z and this arrow represents z plus delta z. So this delta z will be this one, this complex number. This is your delta z. So this point is your z plus delta z. Okay, so when I make a small change in z, then what will happen is the function will also change. So this is your function f of z, this is f of z, and when I make a small change, this point, okay, this is a point here, and when I make a small change in the point, then what will happen is this point over here, it probably, let's say it moves over here. So this function, the value of the function moves to this point, the value of the function moves to this point. So this is your delta, this is your delta f. So the derivative is basically this change in the complex function, that is delta f, divided by this change in the complex variable, which is delta z, and you take this as in the limit as delta z tends to 0. That means you make this change infinitesimally small. So when you make the change infinitesimally small, this change will also become infinitesimally small. And if the ratio of this change by this change, if the ratio, if it exists, then that is known as the derivative of the complex function at this point. Pretty much in the same way as we define real functions. And you can see here what is delta of f. Delta f is the value of the function. What is the value of the function here? This is, what is the point here? The point is z plus delta z. So f at z plus delta z, right? So what is delta f? So delta f will be simply this complex number minus this complex number, which is f at z plus delta z, f at z plus delta z minus this complex number, which is f at z. This is delta f. And similarly, delta z you already know. Delta z is z plus delta z minus z. So when you take the ratio of these two, delta z divided by this point is z plus delta z, and this other point, initial point, is z. So z will get cancelled. We'll just get delta z in the denominator here. So that's the derivative of a complex function. Pretty much the same way as real function derivatives are defined. Okay. So under condition, the limit in okay, one more important condition. The limit in equation number 1, this limit that we have written in equation number 1, it should be independent of the direction of approach chosen to z. The direction of approach, in which direction do you apply? Okay, in which direction you move towards z. Either you could move this way or you could move the other way. In which direction you move, that it is independent of that direction of approach. So this is known as the derivative of a complex function. Okay, any questions? All right. So now we come to important set of conditions, which is known as the Cauchy-Riemann conditions. So Cauchy-Riemann conditions are very important because we use these Cauchy-Riemann conditions to determine whether a complex function is analytic or not. So suppose I have a complex function. Okay, that complex function is f of u, f of z, which is equal to u plus iv. The derivative df by dz, it exists if and only if the partial derivatives of u and v, the partial derivatives of u and v, because remember, what is u? U is a function of x and y. If u is a function of x and y, then u is going to have partial derivative with respect to x, and it will have a partial derivative with respect to y. Similarly, v is a function of x and y. So when moment is a partial derivative, that means it will have a partial, it's a function of two variables. It will have a partial derivative with respect to x, and it will have a partial derivative with respect to y. Okay, so given a complex function, the derivative, this derivative exists if and only if the partial derivatives of u and v are continuous. The partial derivatives, they do not have any discontinuity, and the Cauchy-Riemann conditions hold good. So these are the Cauchy-Riemann conditions. The first condition is the partial derivative of u with respect to x is equal to partial derivative of v with respect to y. And the second condition is the partial derivative of u with respect to y is equal to the negative of the partial derivative of v with respect to x. So if these two conditions are satisfied, namely the first, the partial derivatives, they exist and are continuous, and the partial derivatives, they follow this relation, then we say that the derivative of the function, it exists. Okay, so that's the Cauchy-Riemann conditions. Okay, so then we talk about Cauchy-Riemann conditions, this will help us now to understand what is an analytic function. So what is an analytic function? You all are probably aware of analytic function. You would have probably done this in your BSc course. So analytic function is basically this. If a function f of z is differentiable, if a function is differentiable, okay, and it is single valued, it has got a single valued in a region of a complex plane, then it is said to be an analytic function. So basically, two things it must satisfy. It must be differentiable and it must be single valued. Okay, in a region of the complex plane, the function must be differentiable and it must be single valued. Then it is said to be an analytic function. So analytic function is, if the function is analytic everywhere in the complex plane, then we call it as an entire function. There is no exception. In all parts of the complex plane, the function is analytic, so it's an entire function. Then if suppose the derivative does not exist at some point, the derivative of this function f does not exist, that means it becomes undefined at some point z equals z naught, then z naught is known as the singular point. Okay, just some definitions I'm giving you over here. Then we have the first theorem, first important theorem. The theorem is that necessary conditions for a function to be analytic at all points in a region R are that the Cauchy-Riemann conditions hold good. That means if you want to know whether a function is analytic or not, you just need to check whether the Cauchy-Riemann conditions, which we saw in the previous slide, these Cauchy-Riemann conditions, they should hold good. If they hold good, then we know that the function is analytic, okay, at all points in a region R. Then theorem number two, this is the first theorem. First theorem, what it says is, for a function to be analytic, the Cauchy-Riemann conditions hold good. Second theorem, what it says is, the sufficient conditions for a function to be analytic in a region R, the Cauchy-Riemann conditions hold good, and these partial derivatives, they are continuous, okay, in the they are continuous functions of x and y in the region R. So essentially, together these two theorems, theorem 1 and theorem 2, what they are saying is, if a complex function has got continuous partial derivatives and satisfies the Riemann conditions, it is analytic, and vice versa. That's what these two theorems, that's why it says. Okay, so theorem 1 and 2, what it says is, theorem 1 and theorem 2, what it implies is, if a complex function, if a complex function f of z, if a complex function f of z has continuous partial derivatives and satisfies the Cauchy-Riemann conditions, it is analytic, and vice versa. I mean, also the fact that if you're able to apply the Cauchy-Riemann conditions, it implies that the partial derivatives, they are continuous. Then only you can apply the Cauchy-Riemann conditions. So if you want to check, if I give you a function and I ask you, check if the function is analytic or not. So all you need to do is just apply the Cauchy-Riemann conditions. That's all. Or if the Cauchy-Riemann conditions, I mean, if the function is analytic, then automatically you know that the Cauchy-Riemann conditions will hold good. So really most important over here, the Cauchy-Riemann conditions, okay? Cauchy-Riemann conditions for the analytic function, that is dou u by dou x is equal to dou v by dou y. That's the first condition. And the second condition is dou u by dou y is equal to minus dou v by dou x. Okay. I think I have some problems here. Yes, we can do some problems here to understand this better. Okay, so let's try to solve this. Okay, we have to check whether the following function is analytic or not. Okay, so we'll do the first problem and then the rest of this I'll leave it to you as homework. The function that is given is f of z is equal to 1 by z. We have to check whether it is analytic or not. So let me write down the function here, f of z. F of z equals 1 by z. So this can be written as 1 by z is x plus iy. Then you multiply and divide by the conjugate, that is x minus iy divided by x minus iy. And this gives us x minus iy divided by multiplication of a complex number with its conjugate will simply give us the magnitude of the complex number, so x squared plus y squared. So this is your f of z. So that means this f of z can be written as, I open this up, so x divided by x squared plus y squared plus I into, sorry, there's a minus sign here. I can keep the minus sign inside. So I into minus y divided by x square plus y square. So this is the complex function. Now, if you recall, we were talking about complex functions, and I showed you a complex function. How do we write a complex function? We can write a complex function like this. We can write it as u plus iv, right? A complex function can be written as, let me write down here. Complex function can be written as f of z can be written as u, which is a function of x and y, plus I into v, which is again a function of x and y. Okay, so this is how we can write complex functions. Back to the problem. Okay, so coming back to this problem. So now let's compare these two. If you compare these two, then what conclusions do you draw? You compare with this one, what conclusions do you draw? We immediately see that u, which is a function of x and y, this must be u. This must be u, and this must be v. Okay, so when you compare these two, we have u of x comma y is equal to x divided by x square plus y square, and v of x comma y is equal to minus y divided by square plus y square. Now we have to check whether these are analytic or not. Analytic or not means we have to check for the Cauchy-Riemann conditions. Okay, checking whether it's analytic or not means check for the Cauchy-Riemann conditions. So what is the Cauchy-Riemann conditions? Dou u by dou x, we have to find out dou u by dou x. Then you have to find out dou v by dou y. We have to check if these two are equal or not. That will satisfy the first Cauchy-Riemann conditions. Then you have to find out dou u by dou y, and then dou v by dou x. These two should be negatives of each other. That will satisfy the second Cauchy-Riemann condition. So that means Cauchy-Riemann condition is satisfied. That means they are analytic. So now can you try this? Please find the partial derivative of u with respect to x. Please find out all these four partial derivatives: dou u by dou x, dou u by dou y, dou v by dou x, and dou v by dou y. Please do that now. If you have a notebook, please take out your notebook and find out the partial derivatives. And let me know if any of you have finished this. Just let me know. I'll wait for you to do this. Has anybody completed?
So dou u dx is 1 by x square plus y square minus 2x squared by x squared plus y square whole square.
Dou u by dou x, how much did you get? No, it won't be so. No, not like that. Dou u by dou x is not that. Dou u by dou x will be simply y
Yes, sir.
square minus x square divided by y square minus x square divided by
Sir, I have not simplified
x
it.
square plus. Okay, simplify it, please. This is what you should get.
Sir, actually, it's the same thing. It is 1 by x square plus y square minus 2x square by x square plus y square whole square.
Okay, just simplify it. Simplify everything.
Okay, sir.
Anybody else got the others?
So it is, yes, y square minus x square by x square plus y square whole square.
Okay. Next one. What about dou u by dou y?
Sir, one minute, I'm there. Sir, it is minus 2y by x square plus y square whole square.
Simplify it.
It's simplified it, sir.
Minus 2xy divided by x square plus y square whole square. You should get like this.
xy, sir.
Minus 2xy, yes. Others, are you all working or not? Anybody else?
Actually, I missed that. Yes, sir. It's minus 2xy by.
Then proceed for v. Partial derivatives for v. What about the others?
Next, sir.
Can you show the v function once?
Del V del X.
Which one? Dou v by dou x you're doing. Tell me.
Yes, yes.
What is dou v by dou
Twice
x?
XY. Twice XY.
Dou v by dou x is twice. Really? Oh, yes, you're right. It will be twice
xy
xy.
By
x
X square plus Y square whole square.
Good. And this one?
And it's Y square minus X square. By X square plus Y square whole square.
Okay, so you can see that these two are equal, and this one, they're inverse of each other. So since so we find that the Cauchy-Riemann conditions are satisfied. So CR conditions, the Cauchy-Riemann conditions are satisfied. Okay, and hence, and therefore, f of z equals 1 by z is analytic for all. Do you agree? Because z should not be 0, because if z becomes
Yes,
0,
sir.
then it becomes undefined. If it becomes undefined, then it is no longer analytic, yes or no? So if it has to be well defined, so that's the reason it cannot take any value at 0. So modulus of z is greater than 0. So that's how you need to check for the analyticity. Is that clear?
Okay, sir.
All right. So there are some more problems which I'm leaving it to you as a homework. The rest of the problems. Please do this at home, okay? Please do these problems at home. Check for the rest of the problems. 2, 3, 4, 5, 6, all of them. Just check whether they're analytic or not. Okay. All right. So next, we are talking about this one. Yeah, I think that's going to be the end because there's a few more points. So real and analytics parts of real and imaginary parts of an analytic function must satisfy the Laplace equation in 2 dimensions. What is the Laplace equation? The Laplace equation. Do you remember? The Laplace equation. The Laplace equation is basically the Laplacian of f is equal to 0. And Laplacian is dou square fy dou x square plus dou square f by dou y square, because it's 2-dimensional, so only 2 partial derivatives, no z. Okay, so this is equal to 0. So what it's saying is that real and the imaginary parts of a of a complex of an analytic function satisfies the Laplace equation. The proof of this, okay, is very straightforward, and I would like to leave this proof as a homework for you all. Okay, just show. That means what you have to show is basically you have to show when I am asking you for a proof that the real and imaginary parts of an analytic function they satisfy the Laplace equation. So basically, what you have to show is this: you have to show that dou square u by dou x square plus dou square u by dou y square is equal to 0, and dou square v by dou x square plus dou square v by dou y square, this also must be 0. So both of this must be identically 0. So if these are identically 0, that means you can see this is the Laplace equation. So that means u and v satisfy the Laplace equation in 2D. So this is what you have to prove. Okay, so I leave this to you as a homework. We just try this out. Okay, show that the u and v, the real and imaginary parts of an analytic function, they always satisfy the Laplace equation in 2 dimensions. Okay, and so for this reason, u and v, they're also referred to as harmonic functions because they satisfy the Laplace equation. Laplace equation, those functions which satisfy, they are known as harmonic functions. So u and v, and there should be a v here. There should be a v here. Okay, I forgot to put here. There should be a v here. Okay, they're known as harmonic functions. And u and v again. Got to put a v here. Are conjugate harmonic functions of each other. That is, curves with constant u and v, uv, make orthogonal intersections with curves of constant v. Curves of constant u and curves of constant v make orthogonal intersections with each other. So which I'll probably show it in the next class. Okay. So this completes the first lesson on analytic functions. Okay. Anybody has any questions? Any questions?
Sir. So for the function to be
Larry.
so for the function to be analytic, the main condition is only the Cauchy-Riemann condition, sir.
Yes.
Or continuity also must be satisfied.
Yes, only the CR condition. And you see, the moment the CR conditions are satisfied, moment you are able to write these equations, it's automatically understood that these are continuous now.
Okay, sir. But
Yes or no?
like
If you are able to write equations like this, yes or no? Yeah.
Yes, sir. Like the last example where z is undefined at.
What do you see?
Like the last example, z is undefined at z equal to 0. So I thought.
0. Yes, 0.
At z.
In this case, if we directly, I'm just taking the definition of Analytic function. What is an analytic function? An analytic function is differentiable and it is single valued. Of course, okay. What I get what you're asking. What you're asking is in the problem that we have done, I just stated no that it is not analytic at z equals 0. Yes, there are ways by which you can actually come. There are methods by which you can actually come to that conclusion, and I think those methods they're already covered in your BSc course. So that's the reason why I'm not doing that. Okay. So it's simply just if you can see something like this. Okay. So suppose I see a function like this, f of z is equal to 1 by z minus I, right? So moment I see this, I know that f of z is not analytic. Immediately I get to know that this is not analytic. At which point?
Z equal to I.
Z equals I, right? So immediately we get to know. So this you just quickly follow instead of going through the motions, that entire series of steps for finding which point it is not analytic. You can just directly look at the function and you can find out. So that's what I did in this problem. Otherwise, for analyticity, you just have to check for the Cauchy-Riemann conditions. Okay, does that answer your question, Larry?
Yes, sir. Yes, sir.
Okay, any other questions? Okay, so if there are no questions, then I think we'll stop here. And in the Google Classroom, I'm just going to share that link for attendance. There's a link for attendance. Those students who